An escapade on, or rather above, Mars, this week on Planetary Radio. Welcome. I'm Matt Kaplan of the Planetary Society with more of the human adventure across our solar system and beyond. Yes, we've got yet another visit to the red planet for you. The twist is that escapade, the Escape and Plasma Acceleration and Dynamics Explorers, are budgeted far below a typical NASA Mars mission. We'll talk with Principal Investigator Robert Lillis of UC Berkeley about how his twin spacecraft will help us understand the tortuous evolution of that world. Bruce Betts is anxiously waiting in the wings with a night sky update, one of my favorite space history events, a random space fact, and a new space trivia contest. Can you do me a favor? If you haven't already, please give Planetary Radio a rating or review in Apple Podcasts. Why there? Because it's where the most people listen to great podcasts, but we'll be happy to get your rating anywhere, really. And if you've already done this, thank you. Sad news reported in the September 3rd edition of The Downlink. We learned a few days ago that Carolyn Shoemaker had passed away. Carolyn and her husband Gene worked steadily for many years, discovering hundreds of asteroids and 32 comets. One of those comets would get the name Shoemaker-Levy 9. Carolyn, Gene, and their colleague David Levy found it shortly before it smashed into Jupiter back in 1994. I had the honor of talking with Carolyn at the 2013 Planetary Defense Conference. We've got a link to that episode of Planetary Radio on this week's show page at planetary.org/radio. Carolyn Shoemaker was 92. It happened too late to be included in the downlink, but we can now confirm that Perseverance successfully collected a sample from Jezero Crater on Mars. You can expect this major accomplishment, the first of many collections to come, will be covered here on Planetary Radio and through the Society's other channels. Want to have the downlink sent to you for free each week? You can subscribe at planetary.org/downlink. Space is hard. Mars is harder. Getting a robot there to explore and do great science can cost $1 billion or more. There are things only powerful, sophisticated spacecraft can do, but NASA wants to find out if a much more economical approach might complement the more expensive missions. Enter Escapade, the brainchild of a team led by University of California, Berkeley research scientist Robert Lillis. Rob is also the Associate Director of the Planetary Group at Berkeley's Space Science Lab. I asked Rob to be our guest when I saw a few days ago that his mission had gotten the green light from the space agency. Here's our conversation. Rob, welcome to Planetary Radio, and congratulations on this great news for Escapade. I'm looking forward to your launch, in 2024, if all goes well?
That's correct, Matt, and thank you very much for the kind words. Yeah, Escapade is going to launch sometime in 2024. The launch date as yet and the launch vehicle are both TBD, but hopefully by early next year we will have those details all nailed down, and we're excited to get going.
Not one, but two, count them, two spacecraft for peanuts, really. Under $80 million, as anybody who listens to this show knows, that's nothing for an interplanetary mission. And you're sending two spacecraft. I also got a note, because I'm a UC product, the blue and gold. Thank you for that.
Right. That was actually the project manager, Dave Curtis's idea. He's been at Berkeley a lot longer than I have, but yeah, we're big fans of the Golden Bears, and so blue and gold made great sense. And also, it's just more fun than Spacecraft 1 and Spacecraft 2. So,
No question about it. What's the current status now that you've gotten this go-ahead from NASA?
Right. So this was the major milestone review, or the KDPC, key decision point to proceed to Phase C. Phase C is the detailed design, assembly, integration, test, and then leading into D, which is, I guess, the final integration and then the launch, and then Phase E is the operations, of course. So this is since the bulk of the money is spent in Phase C and Phase D, this is NASA's kind of way of saying, okay, we've seen your preliminary design. We think this is mature enough. This is feasible. We're happy to commit to the vast majority of the rest of the budget. And you have our blessing to go ahead and start moving into the detailed design and build.
I always love to ask PIs, how did you get the word? How did you learn that NASA was saying you are go for launch, essentially?
Well, we were actually in the room. This was at NASA headquarters. There were 14 or 15 of us in the room at headquarters. It was chaired, of course, by the Associate Administrator for Science, Dr. Zerbukin, and there were another maybe 60 people on the line, including all the heads of the different divisions within the Science Mission Directorate at NASA. And so, after presentations, lots of questions. Presentations by the PI, by the project manager, also presentations, importantly, by the chair of the Standing Review Board to say, yea, verily, we believe that this project is sufficiently mature to go ahead. And then several probing questions from Dr. Zerbukin, from the division head for heliophysics, Nikki Fox, the AA for programs, the deputy AA for programs, Wanda Peters, and several other folks online as well. Finally, at the end of a 3-hour meeting, we are officially confirmed, and everyone shakes hands and goes, yay. And then you go for drinks next door at the Hyatt, which is right conveniently next door to NASA headquarters. So it was a joyous moment. And it's one of those things where, the preliminary design review has gone well. The Standing Review Board has told you that it's gone well and that they are recommending that you go ahead. But it's not until all the important folks within the Science Mission Directorate actually get to really examine and ask questions and give their approval that it's all going to go ahead. So that was a very satisfying moment for myself and for the whole Escapade team.
I bet. And I bet it was even more fun than defending your PhD dissertation from the sound of it. Okay, so you celebrated, obviously, and that was very appropriate. But now, is it hitting home that you've got, 3 years to build 2 very sophisticated spacecraft, which I think our audience also knows that's not a lot of time.
It's not a lot of time. And I will say that Escapade is an example of what NASA is trying to prove can be a legitimate model for these sorts of missions, where you accept slightly more risk. You go with commercial partners who have more common off-the-shelf approaches to things, more modular approaches to things, where they, for example, have exactly the same radio for every spacecraft that they make. They're also vertically integrated. I should say Rocket Lab are our spacecraft partners. They have an approach that's really new, what you might call commercial space entering the world of what some people call civil space, scientific space missions. And between ourselves and the other 2 Simplex missions, Janus and Lunar Trailblazer, NASA is sort of conducting the experiment as to whether a slightly higher risk tolerance paradigm can allow for significantly more science per dollar, bang for your buck, call it what you will, but really getting a lot more science for a lot less money. And we're one of the guinea pigs, and we are confident of our approach. NASA wouldn't have passed us if they didn't think so too. So this is going to be fun. I should say that the costs for the instruments are actually very much in line for what we would have produced instruments for in the past for NASA. They are built to print instruments. They are near exact copies of prior instruments, which does bring down the cost. But we're not cutting any corners in terms of how we build the science instruments. They would be built the same way as they would be for a much more expensive mission. It's much more to do with the spacecraft bus itself. That's where most of the savings come from.
I'm going to come back to that, but we should mention that Simplex, this NASA program, is small, innovative missions for planetary exploration. I read that you've complimented NASA for taking this risk with Escapade and the other 2 missions that you mentioned. They are taking somewhat of a risk, but I would compliment them as well.
Yes, I think it is a bold move. It's a relatively small portion of the total NASA science budget, actually. So it totally makes sense, as any savvy investor knows, to put a fraction of your portfolio into something that's a little higher risk and might have a higher return. So NASA is taking that almost investor approach, which is appropriate because NASA is essentially investing our tax dollars in these science missions. NASA has been historically very risk averse. That's understandable. It's a public agency spending public money, and failures are high profile and don't look good. So it takes, I think, that bit more courage for NASA to actually invest in a higher risk. Now, I wouldn't say high risk because we don't think it's high risk. We think it's actually very likely to succeed. It just maybe isn't the 99% or 98%. Like maybe it's in the low 90s, maybe it's in the high 80s. No one knows exactly what it is yet, but it's not much more risky than what NASA has done before. We think it's an appropriate risk versus reward trade-off.
I like that investment philosophy very much. I want to come back to Rocket Lab. A lot of people may think of it as a New Zealand company because that is where they got their start. But now, of course, their headquarters is from my old town, Long Beach, California, a few hundred miles south of where you are at UC Berkeley. And they have, I guess, this standard spacecraft format, this bus that they call Photon. And this is part of what you're talking about, more or less off the shelf.
Yes, that's right. So the Photon bus is modeled on Rocket Lab's upper stage, their kick stage, their third stage, if you will, from some of their previous launches. As you know, Rocket Lab has done 20-ish launches, and a number of them needed an additional kick to a higher orbit. So they have had this kick stage, which before has not had solar panels because it could run on battery power, because it only had to last a few hours. But it had all the same subsystems that a spacecraft needs to get to the right place, to know what its orientation is, to have propulsion, etc. So what they've done is they've taken this kick stage and called it Photon, and decided to essentially sell it as a science platform or a platform for other things too. I know that they have some work with the classified part of the government. I'm not sure what that is, but I'm sure there are other things you could do with this sort of platform. And they're taking their engine. It's called Hypercurie. It's a high thrust, high specific impulse engine. They're adding solar panels, of course, because we need to have a lot of power in deep space. It's becoming a standard spacecraft bus, except at a much lower price point. Another key aspect here is that Rocket Lab is taking a firm fixed price approach, not a cost plus approach to their contracts. Historically, NASA science missions, the spacecraft provider is contracted using a cost plus paradigm, where if it costs more, NASA pays. Rocket Lab thinks that they are essentially selling a service and that the service should have a fixed price. And this is also a brand new paradigm. And NASA has, again, to NASA's credit, NASA has embraced this and said, yes, this is a paradigm we think these low-cost missions would actually really benefit from. We're really impressed with the Rocket Lab team, us at Berkeley. They're very professional. They have excellent systems engineers, excellent subsystem engineers, thermal engineers. They're also very responsive. We're very happy working with Rocket Lab so far, and we look forward to continue to working with them as we get into the real rubber hits the road phase of this project now.
I look forward to visiting them someday at their headquarters down south of you. It really is my old hometown, was for many, many years, Long Beach. And anybody who wants to see an artist concept of the spacecraft, Blue and Gold, the two spacecraft for the Escapade mission, should go to planetary.org/radio and look up the current week's this episode, because we'll have images there. We'll have other stuff about what Blue and Gold will do once they reach Mars, and links to the press release, which is how I learned about the approval of this mission. Lots of other great resources, as always, at planetary.org/radio. You have some other partners in the mission as well. I saw some other academic partners.
That's right. Indeed, we do. So the two primary instruments, the two halves of the electrostatic analyzers, are built at UC Berkeley. That's one of our bread and butter instruments, space plasma analyzer measuring both electrons and ions. But we do, as all space plasma missions need, we need a magnetometer. And we are working with our longtime colleagues at UCLA to provide that magnetometer. This is a magnetometer. There will be one on each spacecraft at the end of a 1.3 meter long boom. You need that kind of boom to get away from the magnetic noise generated by the spacecraft. These are almost carbon copies of the magnetometer on the InSight Mars lander, minus the dust cover. But yes, basically the same sensor. built to print, very, very low risk instrument. And then our other major academic partner is Embry-Riddle Aeronautical University in Daytona Beach, Florida. They are providing 3 different sensors comprising what we call the Escapade Langmuir probe, or ELP. And this is a planar ion probe to measure ion densities. This is a multi-needle Langmuir probe to measure electron densities, and also a floating potential probe to measure the high cadence changes in the electric charge on the spacecraft, which is important for interpreting the other measurements. So it is a small but highly focused four instrument package on each spacecraft, completely identical on both spacecraft, and that's important because you need to make sure that you're comparing apples to apples.
This is a great way for us to begin to talk about the science that blue and gold will accomplish when they're orbiting Mars. And partly as a way of getting into that, tell us a little bit about your colleague who is going to serve or is serving as the project scientist for Escapade.
Dr. Shannon Curry is the project scientist on Escapade. In essence, really one of the 2 deputy PIs, along with the very well-regarded and highly influential and highly well-published Dr. Janet Lumen. Shannon is serving as the project scientist. Shannon is also, perhaps more importantly, has just taken over 5 days ago as the PI of MAVEN from Dr. Bruce Chakosky. So
I didn't know that. Bruce has been on the show several times talking about MAVEN, and I didn't realize he'd handed off the reins.
That's right. Bruce handed off the reins to Shannon. It was about a year-long process of choosing a successor and getting Shannon integrated into all of the different financial, management, contractual aspects of the mission. So Shannon is, I'm stepping into big shoes, but Shannon is well able for it. Shannon has a great head for not only the science, but also the dynamics of how teams work together, science teams, engineering teams, management teams, and will make a great leader for the MAVEN project. So it'll be interesting because when I wear my MAVEN hat, she'll be my boss. When she wears her Escapade hat, I'll be her boss. And that sort of dynamic is pretty common in the planetary science world, which is kind of great because it means that there's always a lot of collegiality, understanding. No one ever gets too big for their boots because, someone's always your boss on something else. It's been working very, very well. And also there's so much synergy between MAVEN and Escapade. And I can get into that a little bit later in terms of the scientific synergy and actually the degree to which MAVEN kind of really set up Escapade and how Escapade builds on MAVEN's legacy. Shannon's going to be a great asset to both the Escapade team and a great leader for the MAVEN team. On top of all the other stuff Shannon does. I mean, Shannon does a bunch of Venus stuff on Parker Solar Probe as well. She has a bunch of students. She does it all.
We don't have to wait. I was going to bring up the fact that you are also part of the MAVEN mission, as well as the HOPE mission, those other Mars orbiters that are attempting to help us understand the atmosphere and its evolution at Mars. How will Escapade complement the work that is being done by those spacecraft and others? And so we will start getting into the science.
So let me start first of all on how Escapade complements MAVEN and how Escapade was really launched by MAVEN. Having been on the MAVEN team since almost the beginning, back when I was in grad school, we had always wanted to understand the upper atmosphere and the plasma environment of Mars, and in particular, the ways in which solar energy in the form of solar extreme ultraviolet or solar wind, the interplanetary magnetic field, solar energetic particles, how that heliospheric environment interacts with the upper atmosphere, the ionosphere of Mars, and in particular, Mars's unique crustal magnetic fields. MAVEN was sort of designed to study how that heliospheric environment, solar wind, solar extreme ultraviolet light, interplanetary magnetic field, solar storms, solar energetic particles, how all those affect the Mars upper atmosphere and interact with it. Mars is really a unique planet. It has what we would call a hybrid magnetosphere. Okay, why do we say hybrid? Because it has many aspects of both an intrinsic magnetosphere, such as the Earth or Jupiter, where there is a global dipolar magnetic field generated within the core. Typically, the magnetic field lines extend far, far beyond the planet and actually stand off the solar wind to a large multiple of radii of the planet. So that's an intrinsic magnetosphere. And then there's also what we call an induced magnetosphere, such as Venus, where there's no global magnetic field, but there is a conducting ionosphere. And so the the plasma pressure within the ionosphere itself can sound off the solar wind, but the solar wind gets much, much closer. And the bow shock in front of the planet, the region where the interplanetary magnetic field piles up against the ionosphere, that's all much closer to the planet than it is in an intrinsic magnetosphere. And Mars has aspects of both, that intrinsic and induced. And the reason is Mars has these very strong, coherent crustal magnetic fields, but not uniformly across the planet. They're isolated mostly in the southern hemisphere, or the strongest of them certainly in the southern hemisphere, and mostly within a relatively narrow band of longitude between about 110 degrees and about maybe 250 degrees east, so that Terra Serenum, Terra Chimeria area of Mars. And there's these strong crustal magnetic fields. And the only way that we can explain them is coherently magnetized chunks of crust, hundreds of kilometers long, tens of kilometers wide, tens of kilometers deep. And those result in strong magnetic fields that can push the solar wind away up to more than 1,000 kilometers. But they're only really on one side at that strength. So as the planet turns, you get very different interactions with the solar wind. And these magnetic fields connect and reconnect with the interplanetary magnetic field. And all that connection and reconnection results in plasma acceleration, which can give us aurora, which we're just starting to understand now. And that also helps to sometimes tear away chunks of Mars's atmosphere. These huge blobs of plasma could just be torn away by these magnetic reconnection events, and that's an important part of Mars's atmospheric loss. And of course, MAVEN's prime reason for being was to understand how Mars lost its atmosphere over time. So anyway, MAVEN has done a lot of work in understanding the different escape processes from Mars, both neutral escape, ion escape, etc. ESCAPADE really, I mean, it can't do nearly what MAVEN did. ESCAPADE is focused on that ion escape piece. When we had MAVEN, we could do a great job of measuring in situ what was going on at any one particular place. It's like measuring the wind. You can't measure the wind just by looking at it from 10 kilometers away, because you can't, unless there's clouds, I guess. But if there's no clouds, wind is invisible. Same thing with solar wind, with the plasma flows around Mars. And so in order to measure it, you've got to be in situ. You've got to be right there. And MAVEN, as one spacecraft, could either measure the solar wind conditions that were driving the system and the atmospheric escape, or it can measure the escape itself. It couldn't do both at the same time. So MAVEN allowed us to build up an average picture of what the atmospheric escape picture looked like as a function of the upstream conditions, but always separated in time by an hour, 2 hours, 3 hours, etc. And so we could never understand that real-time response, because it takes only about a minute, maybe 2 minutes at most, for a big solar wind disturbance to propagate through the Martian system, tear away some plasma, and that rich electrodynamic system, we could not measure the real-time cause and effect. And with ESCAPADE, we're going to be able to do that for the first time, because we'll be able to have one spacecraft in the solar wind and the other spacecraft right where the atmospheric escape is actually occurring. So that's one really important piece of what ESCAPADE is doing. There's a second really important piece, and this is we can separate spatial variability from temporal variability. Okay, what do I mean by that? If you are a spacecraft measuring either magnetic field or ion flux, and you see something change, and you're going in your orbit, you're traveling 4 kilometers a second, and you see something change, you see the magnetic field change, you don't know whether that's a global change that happened everywhere, or whether you've just entered a new plasma region where the conditions are different. If you have two spacecraft in the same orbit, like a pair of pearls on a string, and you observe that change twice with two spacecraft that are maybe 10 minutes apart, you can tell whether it's a global change. Because if it is, it'll happen simultaneously at both spacecraft. If you're entering a new spatial region, you'll be able to see the two spacecraft enter it, or maybe the boundary of that region has moved a bit, and you'll see that too. So separating spatial from temporal variability is something that we can't do with one spacecraft. We have to have two. That's the other main thing that ESCAPADE is going to be able to achieve.
I knew that things above Mars were very dynamic, but on the time scale of a minute or two.
Yeah.
The other thing that occurs to me is, if you have, and I did not know this, most of that magnetic activity in that band, in the southern portion of Mars, concentrated on one side of the planet, it's almost as if you had a pulsar. I mean, something spinning about and affecting on each rotation of the planet wreaking havoc in the atmosphere. It's just amazing to keep learning how very dynamic this planet is.
Yeah, I mean, the more we look, the more we learn. And
Mm.
I'll be honest, as big as, I mean, the Maven team is more than 100 scientists, and we have scratched the surface on a lot
Mm.
of what's going on. Even just with Maven data, there's, I'm sure, plenty more to learn, plenty more PhD theses. It's true, when Mars turns its magnetic face away or towards, or maybe side on from the solar wind, we get a really different plasma interaction, really different rates of atmospheric escape. The models tell us that those rates of atmospheric escape change by a factor of 3, maybe 4 at times, but those are models. And while models obviously are extremely important, we'd love to measure that real time response to those changes in the upstream conditions for times when Mars's magnetic face is in different orientations.
Nothing like getting real data points. Um, does the HOPE mission, that great orbiter from the United Arab Emirates, which we have also reported on this show, does this also figure into this research and complement what you hope to do? And as I said, I know you're part of the HOPE mission as well.
That's right. That's right. Yeah. So the Hope mission is dealing with, I would say, the neutral escape piece of the
Hmm.
puzzle more so than ions. Hope doesn't measure ions, although it is sensitive to very high energy particles that are so energetic they'll go right through a spacesuit and give an astronaut cancer, or they'll go right through the walls of an instrument and produce noise. Hope is measuring those, but those are extremely high energy. That's not really what we're talking about here. Hope is focused on the connections between the lower and the upper atmosphere, and how those connections between lower and upper atmosphere help to drive atmospheric escape, particularly neutral escape. I'm talking particularly the photochemical escape of oxygen. And
Hmm.
when I say photochemical, I mean reactions in the ionosphere result in energetic oxygen that can escape, and that's driven by solar EUV, and then neutral escape of hydrogen as well, which is driven by just hydrogen is so light that the high energy thermal tail of hydrogen can escape. So that's mostly neutrals. Escapade is looking mostly at the ions. Now, of course, what are ions produced from? Ions were once neutrals at one point, before they got ionized. And so the neutral atmosphere that kind of forms the reservoir from which ions come and from which ion escape comes, that is something that Hope is definitely looking at. Things like the abundance of oxygen, carbon monoxide in the thermosphere. It's those same species that can get ionized and result in ion escape. So while the direct measurements from Hope and Escapade, we probably won't be looking very closely at them together like we would with Maven, they all form part of the same dynamic system where the neutrals and the ions play together to comprise this picture of upper atmospheric variability and atmospheric escape. And decoding that whole picture, that neutral and ion component of that escape, is so important to understand, particularly how those two different kinds of escape vary with different solar conditions, with different Martian seasons over the course of the 11-year solar cycle, how they change with dust conditions on Mars, because as we've been learning, dust now affects the upper atmosphere much more than we previously thought. Just in the last couple of years, been a lot of great work on that. So understanding how that all fits together to determine the rates of escape, because unless we understand how the different channels of escape vary with all the different conditions, both planetary in terms of dust storms and also the influences from the sun, until we understand how all that plays together, we're not really going to be able to accurately reconstruct the history of atmospheric loss on Mars, particularly because Mars is obliquity, like Mars is axial tilt, which is currently very close to the Earth's tilt. Earth is 23.2 degrees. Earth is 23.6, I think. Mars is 25.2, very similar right now. But Mars's can change from 0 to 80, and it has over the course of Martian history. And so the atmosphere and climate's going to look real different if you have a 60-degree tilt. And so until we understand these processes very, very well and how those affect atmospheric escape, we can't hope to feed that understanding into the models for how that climate system would have operated under different axial tilt conditions over Martian history, to really reconstruct how Mars's atmospheric loss has changed and therefore how the climate has evolved.
Escapade principal investigator Rob Lillis In a minute, we'll go even deeper into Mars's dynamic atmosphere and learn about other missions that are helping Rob and the rest of us understand the Red Planet.
Hi again, everyone. It's Bruce. Many of you know that I'm the program manager for the Planetary Society's Light Sail program. Light Sail 2 made history with its launch and deployment in 2019, and it's still sailing. It will soon be featured in the Smithsonian's new Futures exhibition. Your support made this happen. Light Sail still has much to teach us. Will you help us sail on into our extended mission? Your gift will sustain daily operations and help us inform future solar sailing missions like NASA's NEA Scout. When you give today, your contribution will be matched up to $25,000 by a generous society member. Plus, when you give $100 or more, we will send you the official Light Sail 2 Extended Mission Patch to wear with pride. Make your contribution to science and history at planetary.org/SAILON. That's planetary.org/sailon. Thanks.
How much closer are we to understanding the history of the Martian atmosphere and, what all these outside forces, especially solar radiation, are still doing to it? I mean, we know a lot more than we did before Maven got there, but clearly there are a lot of questions left.
There are indeed, exactly. When you think about atmospheric escape from Mars and climate evolution, you need to think about the sources of atmosphere and the sinks of atmosphere, and understanding how the sources and sinks of the important atoms, which are oxygen, carbon, hydrogen, nitrogen also, as well, have changed over time. You have to understand how that all fits together, but you also have to understand how the different isotopes of those same atoms have escaped differentially, meaning how much more nitrogen 15 has escaped compared to nitrogen 14, how much more oxygen 18 than oxygen 16, because you can't interpret the isotopic ratios that, for example, the SAM instrument on Curiosity has measured at the surface without knowing about how those constituents escape differently, whether they are the heavier or the lighter isotope. That's sort of another next step beyond even where we are with Maven. So the first thing to do is to understand the processes for how those atoms and molecules escape from Mars, both in neutral form and in ionized form. Then we're starting to understand how they will escape differentially. And then also you need to have estimates about how those ratios were in terms of the sources. So the carbon, the hydrogen, the nitrogen, the oxygen that came out of the volcanoes, and the volcanic outgassing history of the planet is also important. And exactly how much mixing was there between the interior reservoirs of those gases and the atmosphere. And that's also important to understand how to interpret the isotopes that we see. And what I'm getting at here is that you need to come at the problem from two different places. One, you need to say, what are the processes causing atmospheric loss today, and how do they change with the external conditions that we see today? And can we estimate how those conditions themselves changed over history? And the answer is yes, but there's a lot of uncertainty there. So that's never going to get us the full answer, because there's too much uncertainty in terms of how the solar wind itself has changed over time. The other direction that you come at the problem is measuring the isotopes, and all the great work that both Maven and Sam on Curiosity have done in measuring the isotopes. Those tell you, you're like, yes, the lighter isotope is definitely depleted. So certainly some of this gas has escaped over time, because the lighter version of it always escapes more easily. And the ratio of those isotopes is usually different than it is on Earth, indicating atmospheric escape. But until we understand the processes that cause that escape, we can't interpret those isotopic measurements well enough. So we are pretty confident that something like half a bar, 1 bar, 2 bars, in that range, you could even go a little further outside that range, depending on how you propagate the uncertainties, of atmosphere has been lost from Mars over time.
Wow. We should remind people that 1 bar is essentially atmospheric pressure at sea level on Earth. So we're talking a lot of atmosphere.
Right, over the history of the planet. And the other difficult thing is when you say something like we've lost, 10 to the power of 30 atoms over some length of time of, say, oxygen. Oxygen is a component of both water, H2O, but also a component of CO2. We know that Mars has lost water because we know that the deuterium to hydrogen ratio is several times higher than it is on Earth, indicating that plenty of water has been lost. But we also know that Mars had a much thicker CO2 atmosphere in its early history, so a lot of CO2 has been lost. And understanding the chemical pathways that link oxygen, carbon monoxide, carbon dioxide, H2O, and then also things like HCO plus, and there's other so-called protonated ions, how all that atmospheric chemistry works together and how that chemistry changed over time and what fraction of that atmosphere was lost as ions versus neutrals. We're still a long way from unraveling all that. I don't want to call it a mess, but that rich physical chemical system. There's many years worth of work in unraveling how the interior of Mars interacted with the atmosphere of Mars, interacted with the solar wind and the solar UV to drive planetary evolution over the billions of years.
And so in all of this, we also edge closer to considering that greatest question about Mars. Was there life? Were the conditions right for the creation of life? And could it still be hiding out there today? Which I know is something that you've also thought about from the angle of your own research, talking about the radiation environment at the surface and so on. I mean, you've mentioned these solar energetic particles, or SEPs, SEPs, which have been a big part of your work. And you did touch on for a moment there the worries that we have in getting humans to Mars because of the same. This is obviously fascinating stuff to you.
Yeah, it's energetic particles at Mars have been a long time interest of mine. Actually, my kind of introduction to the world of spacecraft missions was as deputy lead for the energetic particle detector on Maven. I built a substantial fraction of that instrument, and it was really satisfying seeing it go to Mars. See it work as we intended it to work, and to measure the spectrum, the intensity of these solar energetic particle storms that happen on Mars. But on Maven, we're measuring that particle environment in orbit. And of course, human astronauts will be in orbit around Mars, and it's important to understand the environment there. But the higher energy particles, I should say, first of all, the particles above about 10 mega electron volts, 10 or 20, will penetrate a typical spacesuit. So any unprotected astronaut will be subject to potentially harmful proton radiation from these SEPs in orbit. You need about 130 mega electron volts, give or take. It depends on where you are on Mars, how much atmosphere happens to be above you. Like at the bottom of the Hellas Basin, there's a lot more above you than there is at the top of Olympus Mons, for example. But on average, about 130 mega electron volts or higher, those will make it down to the surface, and those will cause significant fluxes of harmful radiation. And we've worked closely with the team on the Curiosity RAD instrument. RAD stands for Radiation Assessment Detector at Mars. And over the course of the last, they've been there, 8 or 9 years now, they've measured, I believe, 5, maybe 6 so-called ground level events where enough radiation has reached the surface of Mars from these energetic particles that they've noticed a significant increase in the particle flux at the surface. They've never measured a true whopper on the surface of Mars. We think had it been there in 2003, it would have gone off the charts. The Halloween 03 event is the one that we still talk about in the Mars energetic particle community as being the huge one. But there's this background of galactic cosmic rays which easily make it through the Martian atmosphere, and they're ever present. And the highest dose rate that's been seen by the MSL RAD instrument is about 2, maybe 2 and a bit times higher than that background. So in reality, most of the energetic particle hazard for humans on the surface of Mars, at least in the last 8 or 9 years, has not been from SEPs, because we've had a relatively weak solar max. The solar cycle of the most recent one has been kind of a weak one. So it's those galactic cosmic rays. To get away from those, there's nothing you can do but dig underground. You've got to get about 2 meters of regolith between you and those cosmic rays to reduce the level of radiation that you're getting down to a kind of an acceptable level. And of course, this has implications for how much time human visitors, human colonists should or could spend on the surface of Mars. But just because the most recent solar cycle has been weak doesn't mean that there aren't whoppers in our future, because there have been whoppers in our past. And we're pretty sure that there have been events even since the beginning of the space age. There was an event in 1989, I believe, that would have created a significant cancer risk on the surface of Mars had an astronaut been there and experienced that, just from our modeling. So it's going to be a very important part of NASA's planning for human exploration of Mars.
Not many places around the solar system or the universe that are really that friendly to life as we know it. I ran across something that indicated that maybe you discovered when Mars lost the global magnetic field that has done such a good job of encouraging us to reach the level where we could consider traveling to Mars ourselves. How did you pin that down, and do I have that right?
Yes, I mean there had been estimates of it before I did my thesis, but it was one of the main results of my thesis was that I made a map of the crustal magnetic field of Mars, a particularly sensitive one, using a technique known as electron reflectometry. And I worked with colleagues who were experts in crater age dating on Mars, who were able to look at the density of superimposed craters on any particular region of Mars and say, we believe, based on Apollo samples and radiometric age dating of those samples, and associating those samples with craters on the moon, and extrapolating the size frequency distribution of the impactor population to Mars, able to make estimates of the ages of different places on Mars. And I was able to take this sort of age map of Mars and compare it with a magnetic field map of Mars, which I had made, and looked only at the largest craters, the craters big enough that it would definitely have reset the crater age density of that surface, and also fully reset the magnetization in those areas. And so
Reset just because of the heat and the energy of the impact.
the heat and the shock, exactly. I don't want to get too deep into magnetic mineralogy here, but essentially, very high shock and very high temperature can remove all ferromagnetization from magnetic minerals. And then as those minerals cool below what's known as their blocking temperature, which is related to the Curie temperature that your listeners might be familiar with, as it cools down below that blocking temperature, it acquires a magnetization both in the direction of and with a strength proportional to the ambient magnetic field. So when I looked at the relationship between age of impact basin and magnetization of impact basin, I saw a very sharp cutoff around 4.08 billion years, according to that particular cratering chronology, where every basin older than that was magnetized and every basin younger than that was demagnetized. And that told me that the basins that formed after that, there was no strong, at least, global magnetic field to speak of when those basins were formed. And so this sort of gives you this tie point whereby we estimated that Mars's global magnetic field shut off at that point and probably didn't come back again, at least not within the time frame of those craters. Now, there has been subsequent work done. My colleague, Dr. Anna Mittelholz, who I believe is starting at MIT soon, she's done some work looking at lava flows in a place called Lucas Planum, and she has some tentative evidence that maybe the Mars magnetic field might have turned back on again around 3.7 billion years ago. So there's still some work to be done in understanding the precise timeline of the Martian global magnetic field, but somewhere between 4.1, 3.7 billion years old, Mars lost it, and it didn't ever come back. Now, I'd like to correct a potential misunderstanding that I believe exists in popular culture about the role that Mars's global magnetic field played in protecting its early atmosphere. Based on how we understood this problem several years ago, we knew that a global magnetic field is able to essentially protect much of the atmosphere from being lost via ion escape processes. And that's because the magnetic field lines are closed. Plasma that goes onto those field lines can't escape. It's sort of locked in. However, recently there's been a concerted effort by Dr. David Brain of the University of Colorado. He is leading a multi-institution, what's called a DRIVE Center. DRIVE is an acronym that the Heliophysics Division at NASA runs. I don't remember what it stands for, but he is running a detailed sort of data and modeling effort to look at whether that's really true. Is it actually true that just because the area of the planet that is protected from ion escape, just because that area is smaller, does that mean that the total actual escape rates are going to be smaller? Because if Mars had a global magnetic field, such as we do on Earth, it can absorb a lot more energy from the solar wind because the cross-sectional area that it presents to the solar wind is much, much bigger than it would be with no magnetic field. And a lot of that energy can actually get channeled into the magnetic poles and can result in very strong electric fields that can just rip ions out of the upper atmosphere, potentially at higher rates than they would if Mars had no magnetic field. Now, I say potentially. There's a lot of ongoing work there. Things such as the gravity of the planet and the precise strength of the magnetic field. It seems as though as the magnetic field, if you were to start at a field of the strength of Earth's right now, as you get weaker from that, the rate of atmospheric escape can increase for a bit, but then there's sort of an inflection point, at least this is what some of the models tell us, where the atmospheric escape reaches a maximum, but then as you get weaker and weaker, the rates actually go down again. And so this is all still theoretical. One of the problems is that to get to the kind of scales, simulation scales, you need to accurately simulate these escape processes. Even supercomputers tend to break because you need to model things that are happening on tens of meters scales in 3D over thousands and thousands of kilometers, and even huge supercomputers can't do a great job of that. So there's various ways of parameterizing these processes and ways of getting around those difficulties, but it's a very active area of research. But the takeaway for your listeners is that magnetic fields are not the protector that we thought they were even just a few years ago. It is an evolving field of study, and I read a lot in the popular media that magnetic fields are what protected early Mars from losing its atmosphere, and they definitely played a role. Atmospheric escape was definitely very different depending on both the strength and also the nature, whether it's dipolar or quadrupolar, octopolar. But it certainly mattered, but it's not clear that it actually protected the atmosphere for as long as we think. Because remember, Mars was belching out a whole lot of stuff out of its volcanoes in those first 5 or 6 or 700 million years. And since then, it's been kind of a trickle. So there was a lot of atmosphere being created by Mars during those times when Mars was habitable and was conducive to having life. And the magnetic field, definitely a part of the story, but maybe not what we once thought in terms of a protector.
Absolutely fascinating as the paradigm continues to shift. And by the way, I mean, just give it 10 years and I'm sure you'll have that supercomputer power you need to build those proper models on your smartphone. So at least that's something to look forward to. There is much more to look forward to as we run short of time for our conversation. I was hoping that we could talk about the work that you've done much farther out at Europa, where it has to deal with that moon has to deal with that ridiculously strong magnetic field. But I do want to make sure that we talk a little bit about what's ahead. Obviously, you're looking forward to the launch of those 2 ESCAPADE spacecraft. But you had also mentioned to me some other work that you're doing, which is, I suppose, now being looked at as part of the Planetary Science Decadal Survey. It's pretty exciting stuff as well.
Right, exactly. So Mars is sort of in a different, I would say, a different category to other planets because, I mean, while we don't know nearly as much as we'd like to, and we don't know nearly as much as we do about the Earth, we do know a fair bit more about Mars than we do about many of the other planetary bodies in the solar system. So we're kind of past we're mostly past the discovery phase on Mars, and we're into the understanding phase, understanding this very complex system. And it's complex all the way from the core out to the solar wind, but let's just focus on the climate system at Mars. So as part of the Decadal Survey, NASA asked for ideas in a program called the Planetary Mission Concept Studies program, which was in advance of the Decadal Survey, whereby teams of scientists would work with teams of engineers from JPL, from APL, from Goddard, to flesh out ideas for big, like $1 billion plus planetary missions. And NASA selected 11 of those. and they span the entire solar system from Mercury all the way to Pluto and beyond. But two of them were two of the selectees were Mars, and one I was arm twisted into leading a team of 50 scientists and to organize this concept study effort, and it was called MOSAIC, or Mars Orbiters for Surface Atmosphere Ionosphere Connections. And it's that connections, that C at the end, which is the important thing, because there are connections between many of the different regions, or you could call them reservoirs, of the Martian climate system, all the way from the shallow subsurface ice, which interacts with the surface ice, which interacts via sublimation and deposition with the what's called the planetary boundary layer, or the lowest layers of the atmosphere, which interact with the water cycle, with the CO2 cycle, with the dust cycle, especially within the lower atmosphere. And as we're now learning most recently, that dust can be lofted to much higher altitudes, leading to water being lofted to much higher altitudes, which can drive the rates of atmospheric escape up by factors of 10 or 20 when you get a dust storm. Atmospheric waves that originate in the lower atmosphere can go propagate upwards and lead to changes in the loss rates of oxygen. So there's this just series of connections all the way from the ice all the way up to the solar wind. And in order to understand that system and how it interacts, you need to make simultaneous measurements of all of it at once. And so our idea was to send no less than 10 spacecraft to Mars, an armada, if you will, to measure this climate system. And our mission concept was not solely focused on science. It also had significant applicability to the human exploration of Mars, too. We had a whole separate set of science goals, exploration goals. And those exploration goals were to map out the accessible ice, because in order to make propellant, to make air, to make water, you need ice. You got to know where the accessible ice is. And the radars that have been sent to Mars up to now do not have the resolution in the shallowest 10 meters to do that. So radar mapping of ice was a big part of that. Understanding wind. We've never measured wind except by rovers on the surface of Mars. We don't know what the wind fields of the Martian atmosphere are. We have ideas from models, but never measured wind before. So we're going to send instruments to orbit Mars to measure the wind. We've never measured the wind in any part of the atmosphere, really, from the surface all the way up to the thermosphere, up at 150 kilometers. I should say MAVEN has measured a few winds in the upper atmosphere, but nothing systematic. And so this measurement of the atmosphere, the ionosphere, the surface, the solar wind, the exosphere, the rates of atmospheric escape, all simultaneously, as well as measuring the radiation environment in orbit, which, as we mentioned earlier, is relevant for human exploration. For measuring the ionosphere, that matters for human exploration because GPS doesn't work unless you have a very good model of the ionosphere, because the ionosphere distorts GPS signals. It also distorts any kind of communication signals between the Earth and orbit. If you want to use a shortwave radio and bounce your signals around the world, it bounces off the ionosphere. It travels within the cavity between the conducting surface and the conducting ionosphere. If you want to do that on Mars, you have to understand that ionosphere. And so really understanding the short-term variability in the Mars ionosphere was another big part of MOSAIC. And I should also, let's loop back to ESCAPADE. One thing I didn't mention earlier is that ESCAPADE, those Langmuir probes, will measure for the first time the short-term variability of the ionosphere, which is an important piece of characterizing it sufficiently to make a GPS system, a global navigation system, work on Mars. And obviously that's off in the future, but I don't think it's that far in the future. So it's going to be an important piece of the habitation of the red planet. We're excited to be a part of that, both with ESCAPADE, with HOPE, with MAVEN, and in the future, hopefully with many other orbiters and also landers to better understand this uniquely complex climate system that Mars has.
A great place for us to end. Thank you, Rob. It has been delightful as we consider the past of Mars and the future of science and exploration on the red planet. I hope you'll come back. We can talk another time, maybe, about looking farther out in the solar system and about the dangers those present both to robots and to our frail human bodies as we look outward from our pale blue dot. Best of luck. I'm sure we will definitely want to talk again when the blue and gold, those two components of ESCAPADE, are ready to head for the red planet.
Well, thanks a million, Matt. I'm a huge fan of the podcast. I love what you guys do here, and I would be delighted to come back when we're a bit closer to launch, maybe just after launch or something. That'll be great. Thanks.
Thank you again, Rob, for those kind words, and also for taking some time out from your vacation. Go off and have a good day.
Cheers. Thanks, Matt.
Escapade Principal Investigator Rob Lillis is a research scientist at UC Berkeley, where he is also Associate Director of the Space Science Lab's Planetary Group. Time for What's Up on Planetary Radio. I am joined by the Chief Scientist of the Planetary Society. He is also the Program Manager for LightSail, the LightSail program. And if you missed it, you can still watch on demand the documentary made about LightSail 2 and our whole program. It's at youtube.com/Planetary Society, and you are prominently featured. Welcome.
Thank you. Yeah, it was fun.
Yeah, it's not only the documentary, but the little Q&A that you and Jennifer Vaughn and Bill Nye and I did afterward, which was a lot of fun. But I just watched the documentary for like the 5th time last night because my wife had not seen it. And it was just, it's all 5 times. Absolutely delightful. Just lovely.
It is. It's wonderful.
Here's one of those segues. I know what else is lovely.
Oh, me?
Yes, of course.
All right. How about the night skies? So in the west,
How about it?
in the early evening, we've, of course, got super bright Venus. But if you look to the lower right of Venus for the next week or so, you might see the bluish star Spica. And if you look to the lower right of that, Mercury making a guest appearance in the sky. Mercury's looking pretty bright, but you'll have to have a really good view low to the horizon relatively soon after sunset. But you can look to the other part of the sky over there that'd be the east, southeast, and you've got really bright Jupiter and to its right, yellowish Saturn. So a good evening planet sky. We've also got the moon, the crescent moon, joining Venus on the 9th of September and joining Saturn on the 16th and Jupiter on the 17th.
Get under those skies. We got nice clear skies lately here down in the San Diego area, and Venus is still beautiful.
Yep. On to This Week in Space History. It's one of your weeks, Matt. Do you know what it is?
I do. Ba, 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 da, 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 da.
That's right. 55 years ago this week, Star Trek premiered.
Still going strong, I think.
And speaking of something else still going strong, 5 years ago, OSIRIS-REx launched to the asteroid Bennu and is now headed back towards Earth carrying samples of Bennu.
Chock full of bits of asteroid. Yeah, very cool.
We move on to random space fact.
Sort of a tired lion. Couldn't quite find the energy to roar.
So some stars are big.
Yes. Thank you for that fact.
You're supposed to say, how big are they?
Oh, right. I missed my cue. How big are they?
Well, one of them, called Stevenson 218, is so big.
How big is it?
That it's about 2,150 times the radius of the sun. That's about, if you dropped it in our solar system, it's about the orbit of Saturn, filled with just a star, which, by the way, is a volume about 10 billion times the volume of the sun, which we've already established is big. So this is way totally big.
By next week, I want you to tell me how many Earths would fit inside that star, because we know it's 1 million, roughly, inside our own star, inside the sun. Don't think about it now.
10 quadrillion.
You just did the math. You did, didn't you? Very nice. Thank you. Thank you very much. That'll do. That's enough Earths.
I think I got it right. 10 to the 9th, with 10 to the 6th, 10 to the 15th, 10 quadrillion. Whew, that was exhausting. Now do I have to do it next week also?
Yeah, please.
All right. But in the meantime, let us go on to the trivia contest. And I asked you to name every type of spacecraft that has carried humans into Earth orbit or beyond as of now. How'd we do, Matt?
It's pleasing to see how many people were able to answer this just from memory. Now, the total number of entrants was down a bit, but I'm proud of those of you who entered, and especially those who Just pulled it right off the top of your head. Now, a few of you counted Skylab and the Apollo lunar module, but not exactly. If you listen carefully to the question, which was what, Bruce?
It's types of spacecraft that carried humans to orbit or beyond. That kind of got added.
Which Skylab and the lunar module did not do.
No. We were looking for just the things that took them into space, into orbit, into, not just suborbital. Okay, how'd we do? Tell us more.
I will, in this response from our poet laureate, Dave Fairchild. Vostok and Mercury, Voskhod and Gemini, Soyuz, Apollo, the Space Shuttle 2, Shenzhou was followed by Crew Dragon, Spacified, 9 different spacecraft, all orbiting you.
Whoa.
He's right?
Yeah, very nice. 9 types.
Thank you, Dave. Those are also the 9 that were named by our winner this week. Long-time listener, first-time winner, Bill Gowan in North Carolina. Vostok, Mercury, Voskhod, Gemini, Soyuz, Apollo, Space Shuttle, Shenzhou, and Crew Dragon. So congratulations, Bill.
Yeah.
You are going to, you'll have your choice of those robotic spacecraft posters from chopshopstore.com, where all the great Planetary Society merch is, and lots of other stuff too. There's some great new ones as well in that new series that Chop Shop is closing out its Kickstarter campaign. Already successful. They're in a stretch goal for those new robotic spacecraft posters. Anthony Lewis is one of those who got it from memory. He's in Nevada. He says, hopefully these 9 will soon be joined by Starliner, Orion, Starship, and Gaganyaan, which is the capsule that India has been working on for some time. I think they just delayed its first launch into next year, I bet. Ian Gilroy in Australia, very tempted to add my childhood fictional favorites, Thunderbird 5 and the Jupiter 2, which carried us into space in our imaginations.
Entertaining, but not really part of the answer. I don't have to specify in reality, do I?
No, you don't.
IRL, everyone. IRL.
Thunderbird 5, of course, you could see the strings that held it up, just like a real spacecraft. Gene Lewin in Washington is another poet. And this one goes a little bit long, but Shenzhou, Vostok, Mercury elevated humans to apogee, Soyuz, shuttles, and Gemini to the thermosphere. These ships did fly. Voskhod is one of the current 9, bringing folks up past the Kármán line. Crew Dragon also completed this feat with Bob and Doug in commercial seats. And lastly, Apollo went to the moon, and with Artemis, we may return there soon. Finally, Daniel Huckabee, also in Nevada. Go humans! To the stars we go.
Go humans!
We are ready for yet another one of these wonderful contests.
Talking Dawn spacecraft who visited Vesta and Ceres. What fuel did the Dawn spacecraft use for its ion engines? And in kilograms, how much of that fuel did they launch with? Go to planetary.org/radio contest.
Can I say that mission manager or chief engineer Mark Raymond, you are not to enter this one. You are overqualified.
Oh yeah, we've had that problem before. Yeah,
constantly. So here's the prize for whoever gets chosen by random.org and has that correct answer for us by the 15th of September at 8 a.m. Pacific time. It's a brand new book. I think it comes out this week or just came out in the Little Leonardo series, Fascinating World of Astronomy by astrophysicist Serafina Nance, illustrated by Greg Paprocki. Definitely for the younger set from publisher Gibbs Smith. That's what we've got waiting for you, our winner of this new What's Up Space Trivia contest.
All right, everybody, go out there, look up the night sky, and think about how noble are noble gases. Thank you, and good night.
That's Sir Neon to you. He's Bruce Betts, Chief Scientist of the Planetary Society, who joins us every week here for What's Up. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by its generous members. You can learn how to become one of us at planetary.org/join. Mark Hilverda and Jason Davis are our Associate producers Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. Ad Astra.